Welcome back, everybody.
Hi, Jesse.
How are
Good
you
morning.
doing?
Good. I missed your presentation at WKU. I apologize. I was
Oh,
in a conference with the students, so I heard a lot about it, and that's why we're pushing this workshop for the whole entire WKU. So we'll see.
wow, wonderful. I'm thrilled. No, that was it was a pleasure to be able to visit.
Thank you. Thank you. We will work together, so I will reach out after the camp.
Excellent, very good.
Thank you.
All right, folks, we're gonna be getting started up in just a few minutes. We're gonna give folks a few minutes after the hour to get on. So let's go ahead and give folks until about 2 minutes past the hour. Welcome, folks. We're going to be getting started up in just a few minutes. We're going to allow people time to get logged in. We're going to give folks about another 2 minutes to get here. Uh, I had to miss some of the sessions uh, on Wednesday. I would very much love to hear from folks. What did you take away from Wednesday's session? So who'd be willing to share just a little bit about what you took away from Monday and Wednesday's session of last week? Manish, can I call on you? Were you part of the session on Monday and Wednesday of last week?
Yes, I actually came on Wednesday. Um, Something I took away on Wednesday is that you can use AI to quickly prototype like ideas and build MVPs. And so
Yep.
like what would usually take like 1 or 2 months can be reduced to just a couple hours. And I thought that was amazing.
Absolutely. No, I agree. And really the development of that has been really quite striking over just the last few months. As a matter of fact, that's what we're going to be talking a lot about today. So I'd say let's go ahead and let's kick ourselves off. Um, so I'm Jesse Spencer Smith. I'm Chief Data Scientist and Director of the Data Science Institute at Vanderbilt University, also Associate Dean for Partnerships and Innovation for the New College of Connected Computing. Uh, we're going to be talking today about AI models, how give you an idea of how they work, where these capabilities come from. Manish was just talking about, for example, the ability to quickly code up solutions and provide us with software solutions that previously would have taken months, but now can actually be done sometimes in the matter of hours. So let's go ahead and first talk about some of the let's talk about some of the basic models that we've worked with before. I'm going to ask you all questions sort of regularly throughout. You'll know that I'm going to pause and wait for somebody to answer because I'll break out my tea here. So I first would like to ask a question. Many of you were there for Monday and Wednesday of last week. Uh, I just want to get an idea of what's are some of the things that you've been using AI for. Could be programming, could be anything. And you can answer either in chat or you can unmute. It's kind of cool if you unmute some too, so we can hear some for some folks.
Jesse, I can go.
Please.
Okay, so I have been using AI for image recognitions. Long time ago in 2010, like I had a couple of brain scanning images. I wanted to find the disease. AI was in a good place at that time, but couldn't handle a large amount of data. Like we didn't have the GPU, we didn't have capacity for images. So I am bringing back, since with this AI now, and
Mhm.
generative AI, I'm bringing back all the projects, put them back in place. Yeah, that's it. So more it's
Absolutely.
image classification and labeling. That's it.
Got it. Okay. And Lily, I'm glad that you brought up, we've had AI for a number of years. So if it was 2000 or 2010, you might have been working with convolutional neural nets or even before then. So, we've sort of, what we're working with now is transformer models. Convolutional neural nets, creating the revolutionary ability to work and to do pre-training on vision. Is that what you were using?
Yes, exactly. Yeah.
Yeah.
So in the time being, I was like before this evolution of generative I would say 2020,
Yeah.
I would have to label every image I get,
Label.
the
Yep.
disease, the kind. Now I see like this is taking advantage now from it to change all my methods of
Yeah.
manually labeling.
So what's happening now is now we have here I'll back up one. So we have transformers, we have large language models in particular, which are trained on immense amounts of text. We're talking now about trillions of tokens. So this is pretty much everything which is available, either legally available or illegally available on the internet. These models are trained on, and transformers are general purpose learners or powerful general purpose learners by training on immense amounts of text and by having by training on immense amounts of text, it's able to learn very broadly about the world without having to go through that manual process of labeling. This is called self-supervised learning, and we may return and talk a little bit about how that training works. But the important take-home message here is transformers are general purpose learners. They're great learners. The more data you train them on, the better they do. Um, and let's see, Sarah, you mentioned that you use them to prepare for job interviews, generating questions based on job description. That's great. So what you do is you're putting in a context, and then something happens and it's giving you some output, right? So you put in job description and then you ask it questions, or you say, ask me questions. And what's happening with this is that it is taking the text, and we're going to talk about this step in just a moment, but it's encoding it some way. And then in the decoder stacks, it's pulling what it knows and applying this to what you've given it in order to make some type of meaningful output. So that's the highest level. You're giving it context, the questions, job descriptions, and you're asking it to do something. It does something with all of that and then starts answering. So that's the highest level. And then right now we're going to circle down to a little bit closer to what's happening. You put in the context, job description, ask it to do something, and it generates a single token, one word. So a token is a word or subword, which can be mapped to a word, and it only produces one. So let me ask you, how do you suppose that you get longer responses then out of the models if all that it's doing in this one step is producing one token. What are your ideas? So maybe you say use more tokens. Could be. Question is how. Okay, so you might add tokens. Okay, could. More compute, absolutely. Can one token present multiple ideas? Well, each token represents something very rich, absolutely. Have you seen, Thad, there we go. So, have you seen GPT-4o, especially GPT-4o, because it's slower, when it's responding and it begins to respond and it says, and it actually is like producing text, but it's not really fast. What you're looking at there, right there is tokens being produced and turned back into words. And that you put your finger right on it, iterating loops. So what you do is you auto-regressively take this next token and you put it back in the context. So you produce one token, you put it back in the context, and then you rerun the entire thing. This is called autoregressive. So the model, when you were watching GPT-4 sort of produce words, it is auto-regressively taken what your context was, tacks that one word onto it, and then goes back and then reruns. This is how the models, AI models work, generative AI models work. So it's called autoregressive, and it's kind of intensive work. But let's see, who was it that said compute before, more compute? Um, uh, Manish, yes. So here's the thing you remember. Tokens and token production is compute. Token production is compute. When it produces a token, it has done work. It has actually interpreted everything that was in the context, added richness to it, and made a prediction about what makes sense for that next token. Then it takes that, puts it back into the context. And that may change things, right? Now that you're looking at all of that context plus that next word that you've chosen, that may change the meaning a bit. And so then it reruns to see what the next word might. So some of you who are a certain age might remember a particular form of speech, sort of a sarcastic speech from a few years back, and it was kind of mean. You might say something nice about someone. Um, oh, I really like your outfit today. Not. You might remember that. And that changed the meaning of everything that came before, right? Once you put that not, then you realize that the opposite of everything that you just said. So that sarcastic negation of everything that just came before is an example of what can happen here. So maybe this very next token, when you put it back in context, changes everything that came before it. But at the very least, even if it doesn't change it, it informs it. So now we've taken the next loop into understanding what's happening with these models. So it works auto-regressively. But we've covered up a lot of what's happening here. So let's dive a little bit deeper. So let's add some more detail here. Let's talk about what's going on here. Context, next token. These get broken down into tokens. These are words or subwords which break up that text into word or subunit or word subunits called tokens. Tokens are really just integers. It's just like a way of identifying what that text is. And then you get what's called a token embedding. So each token gets mapped into what's called a high dimensional semantic space. Every token gets projected into this space. One example that I tend to use is the idea of king. So maybe there's a particular sentence in here and it has the word king in it. So king maybe gets mapped to this token right here, and then king gets mapped to this embedding. That embedding is just a location in a high dimensional space. And locations have meaning in this high dimensional space. So if you have the word king absent any other context, it's sitting right here. Um, What are some words that you suppose are close to the word king? Oh, I love that. Prince, Aaron, I love crab. Yeah. Ruler, queen. Yeah. Yeah, absent anything else, unless you're a real lover of seafood, it's probably going to be like crown, royal, something like that. Fantastic. Exactly. Those concepts are nearby. We can do math in this high dimensional space. So I can do things like here's woman, okay? Here's uh, man. So I'm going to take king and I'm going to subtract man from it. I'm going to end up right here. What is king minus man? What words are close to king minus man? It could be queen. Yeah, it could be prince, maybe, although prince is male, right? And remember, we haven't added, so it's not quite queen. I think monarch. Oh, that's a good one. Monarch, ruler, crown. Yeah, right. It's not gendered, but it is still ruler. Okay, now what I'm going to do is I'm going to add woman to it. So now I have monarch, crown, ruler plus woman. And now do I have? Yeah. Yep. Now I have queen. So that's what these That's what these embeddings are. This is their locations in this high dimensional space. This is before they're informed by anything else. So that informing, that enrichment of their meaning happens here, and the decoder stacks in some magical way. We'll talk about that in one moment. Then you get to a point where you have hidden states, and from that you produce the next token. Okay, so now we're at a deeper level of understanding. Text comes in, it gets turned into tokens, you get the token embeddings. Something happens to enrich those things, and then you make the guess of the next token. Now, let me pause here and take other questions that you had. There was one good question about other language learning. Would you mind coming off mute, whoever asked that, and ask your question? Oh, Lily, I think you were asking the translation question. Would you mind coming off mute and asking that question?
So I thought when you were asking about how come one token can produce multiple tokens, in my head was languages such as
Oh,
Chinese. English, one word, one token can be translated to multiple tokens. So that's what it was.
right. But actually, you touched on something really important here. And that is, I've been using English because that's my main language, but you're not limited to English here. What you are limited to here is that whatever language you have has to have a really good tokenization scheme in order for it to work. This was a problem with early models. And so it would be English first. And so the tokenization scheme for, say, Arabic was terrible. Therefore, it took many tokens to represent what could be a single word in English. And that would cause problems. That means that meaning would be stretched across many different token embeds. And that was really tough. So that you're asking, does uh, let me go ahead. Um, Likely future words. Now the context doesn't context is just going to be the text that you've been to the model. Um, any anticipation of future state is going to happen here in the decoder stack, and we're going to talk about where that comes from in just a moment. And our embeddings vectors or scalars, they're vectors. So they are vectors in a high dimensional semantic space. So one way of thinking about them is as a location in a 700 or multiple thousand dimensional space. That's how you think about these embeddings. All right, let's go down to the next level of understanding then, unless there are any other questions. All right, let's fill in some of the missing detail here then. Ooh, and Sanjana, that's a great question. Token, I see, this is perfect. Token embeds right here. Okay, you take context, the context gets turned into tokens, you get token embeddings, but you want to remember about where in the sentence that thing occurs because positions are important, are they not? Positions, they are not important. The position of that sentence mattered a lot, right? In one of them, I'm saying, hey, they're important. But if you simply change the order, but you keep the same words, it reverses the meaning. So positionality is very important. Um, in other languages, they may not be as important, absolutely. But even then, you have to know where did they belong? Was it in the first utterance or the second utterance? Because maybe you have many different sentences. So you got to know broadly where they fell. So that's the position embedding. Um, I'm going to make an offer for those of you who are faculty, staff, and students at Vanderbilt University. If you, we're going to get one more level of understanding here, but then we're going to stop. If you want to get really into the where the architecture of these models and how these models work, I do offer a class every semester. I welcome people to audit the class, and this is called Generative AI in Theory and Practice. So we'll get down to a certain level. I'll have resources that I can share with you as well. But we'll probably stop at this next level. But do know you can fully understand this and get a good pseudocode description of algorithmic description of what's happening here and have a full understanding. But the understanding you're going to end on here is going to be not bad. So we have a way of putting some positional information into those embeddings. It's like a little bit of salt. It tells you a little bit of a flavor of where they were. Was it close to the, in? Notice these two things I filled in now. That middle part. The middle part, we have two different processes that happen in each of these decoder stacks, and there can be many of these decoder stacks. One of them is attention. And with attention, every token influences every other token. Because in a sentence, to understand how we mean to use king, you have to know what the other words are. So here's a full phrase for you. She looked across the board and said triumphantly, "King me." Were we in the right place where we put king before in this multidimensional space where it's close to ruler, regent, prince? No, we're in the wrong space, aren't we? We're like, so first of all, she looked across the board and said triumphantly, "King me." Is that king a noun or something else? Yep, Michael, you're right. It's a verb. So we got to be someplace else in this space. Um, what are we talking about here? Give me sort of the general context of what we're talking about. So the word belongs someplace else. What is it? What is what are we talking about here? Are we talking about rulers? What are we talking about? We're talking about games, checkers. That's it. So it's a verb, and we're talking about checkers. So first of all, in the attention, we need that word to be informed by other things going on in this sentence. She looked across the board. So could be game board, but so it needs to be informed by board and said triumphantly. Okay, triumphantly is kind of important. King me. All right, so now board triumphantly and king me. All those are important because it tells us it's being used as a verb. She's winning, and there's a board. That's probably a game. So all of those words need to influence. And what's going to happen is we're going to take this position. Remember, we have all these lovely token embeds. We're going to average some of them, weighted by how close they are, how important they are in the sentence. And we're literally going to be doing an average. We're going to drag that king to a new location. So here, the king is now, that king embedding token is now sitting over here. And it's been influenced by board. It's been influenced by winning. It's by triumphant. It's been influenced by being a verb. But now we need to apply some of the knowledge. So I asked you, what are we doing here? We know that it has to do with these things, but what are we doing here? Ryan, you immediately said checkers. right? Games and checkers. That's the role of the MLP, the multi-layer perceptron. The multi-layer perceptron knows about this position and enriches it further. So you might be sort of close to the idea of game and things like that, but it's going to drag it even further and say, oh, not just any game. This is most definitely checkers. Why? Because of all the things around it. So this is checkers. Now we're talking about checkers. So that's going to happen in the stacks, and then you're going to take those new positions, the new locations for all these, and feed them to the next decoder stack. And it's going to do a further refinement and a further refinement until it has a really good representation of what's going on in this context. And Daniel, you're asking, is there some formal recognition? If it is useful, it will be learned. We're not talking about learning here. We're not training these models right now, but they are powerful general purpose learners, which means if parts of speech are useful, it will learn them. And it turns out, yes, they are useful. So when you train the models, the general purpose learners, so it learns semantics, it learns parts of speech, it learns pretty much everything you got to throw at it. We'll go through an example of this in a moment so you can get an idea of what that training looks like. So all of it's been enriched. Now we have these hidden states. So now here's something that I've hidden from you. And that is, it's not actually producing the next word. In actuality, what it's doing is it is producing a list of all probabilities over all possible next tokens. So if we take the sentence, she looked across the board and said triumphantly, king, to guess that next word. Well, given all the context before, and the fact this is at the end of the sentence and that the word king is looking more and more like a verb, me is going to have a high probability as being the next word. But all other words are possible too. You could have a garden path sentence. So those are possible, but they have much lower probabilities. So, but you don't have to choose the most probable next word. As a matter of fact, we usually don't. Turns out that if you always choose the most probable next word, then the words that you choose, well, there are a lot of uhs in there because we tend to say a lot. We tend not to write it a whole lot, but we say it a lot. We have it turns to be boring. It turns out to be not imaginative. It turns to not be all that useful. So we add a little bit of noise at this point. At this step, when we look at the token probabilities to guess the next word, we actually select the word that may not be the highest probability. Well, actually, what we do, we add a little bit of noise, is if me is like so far ahead of all the other ones, you're just probably not going to choose something else because the probability of me being the next word is so high, the close second is way down there, you're probably going to end up with me. But this is, sometimes we talk about this as being temperature, but this is why when you put in the same prompt into GPT-4 or some other model, you get different results each time because we, on purpose, add noise at this point. So the model can do more creative things. Because remember, we're doing auto regression, right? So we're choosing this next word and then we're going back and we're putting this in context. That's causing the model to walk a different path on its way to solving the problem. With noise, I mean, there are a number of ways that you can add noise. Um, there are some prototypical ways, but you can think of this as quite literally just adding some random numbers to this. You could turn this into an algorithm where you say choose from among the top 10%. Um, but there is a particular way to do temperature. I might do that during office hours today if I could, just because that's going to get into the formal algorithms. All right, other questions before we get before we continue on. Okay, so Sanjana, um, you're asking the position that's being taken into account is actually the position in the phrase itself. She, position one, she looked across the board and said, triumphantly, king me. So it's actually the numerical position within the context. That's the position embedding that's happening there. Because we need to know whether it was the first word, second word, third word, fourth word, and so on. So that's what I mean by positional embedding. So we don't lose that information, because right now, if we don't do that, then it's like a bag of words, which we know doesn't work. And noise, when you're choosing the next word, is indeed randomness. So to review real quickly, put context in, context gets turned into token encodings. Those token encodings get turned into embeddings. That's their initial location in the space. We put a little bit of additional information so we can figure out where they came in, where that embedding was. Was it the first token, the second token, third token, fourth? With attention, all token embeddings begin to inform each other. It's a weighted average where the weight is determined by how close these vectors are to one another. And quite literally, everything moves a little bit. Everything gets shifted around in that space a little bit. That's what attention does. Then the MLP goes ahead and informs that further. Oh, you're in this part of the space where they're talking about checkers. I know all about checkers. I'm going to move you a little bit, and so you're closer, and it makes more sense where you are in that space. Get your hidden states. You get your token probabilities. It produces probabilities of all the next possible tokens, and then it's the next token by adding a little bit of randomness. That's right. So we're going to simplify this a little bit. We're going to leave out the token probabilities here from henceforth. So I'm just going to jump directly to next token. And Joyous, you're asking, does it show how the position is important? Now, words and sense can affect each other. Yeah, position turns out to be important. Position turns out to be a tough thing. And actually, that was it turned out to be important to the advancement for long context models to have a different way of encoding position. And I'll be happy to answer that question in office hours immediately following this. So a key, the dimension of token embeds and position embeds is the same. Yeah. See those little plus? That's a hilarious thing to me. You quite literally are adding the position embeddings. It's the funniest thing. But yeah, they have to be the same dimensionality. I love that dimensionality turns out to be a really good way to track what's happening with these models. So things have to be the same size or the right size to add or to multiply. Underneath all of this is matrix algebra. It's all matrix algebra. So broader context for all of this is all deep learning. Actually, it's kind of standard deep learning, but it's arranged in a particular way, which has turned out to be remarkably useful, remarkably robust. All right, other questions before we jump in and we start talking about how to make these models better? Okay, so Sanjana, do the vector positions reset once a new sentence is read in? Yeah, so here's the funny thing. Once you add another token, either because you're producing a token and adding it in, um, then yeah, everything resets. It's like you just start over. So in one sense, it's like, really inefficient. Um, But that's why it takes so much compute to actually run these things, because it is redoing all that matrix algebra, rerunning all those matrix multiplies rather. Uh, because remember, this next token can really change what the meaning of that previous context is. And make sure you ask how many decoder stacks you have. That is a good question. So, how do you suppose you could make these models better? So, if you wanted the model to do a better job to uncover meaning within a context, and you could sort of change the architecture however you wanted to. Manish, what do you suppose would happen if you added more decoder stacks? If you redesign this architecture Yeah, you add more sex training from scratch again, but yeah, it gets more context sensitive. Exactly. So as you add more decoders, the model's probably gonna be able to do a better and better job. But this comes at a cost, right? That means more more parameters. So attention and especially the multi-layer perceptrons take up space. These are deep learning models. That means uh, these are matrices, and so it gets large. So as you add more decoder stacks, the model itself grows in size, takes longer to train and longer to run. So yes, you can add more stacks in order for it to do a better job. Notice that the multi-layer perceptron, that's going to be where things are enriched. So if I want a model to know more, what could I do for my multi-layer perceptrons? So remember, I was able to add more decoders. What do you suppose I might be able to do? And sometimes this is called a feed-forward network. But if I want the model to be able to know more and to represent more, what might I do with my MLPs? So I actually, Manish, that's not a bad idea to increase context size. I'm going after, absolutely. We're going to return to that in just a moment. Absolutely. What else could I do? These are, this is where the knowledge of the world is stored. It's stored here in these MLPs. And give me a thumbs up on this. Do I have your permission to call on you all to see if I can get some more suggestions? And you can always pass, but give me a thumbs up if you're good with me just calling and you can say, I don't know, can I pass? Okay, Ryan, give me thumbs up here. Okay. Oh, Dan, wrong answers are perfect. Wrong answers are great. All right, so some buy-in here. Okay, great. Thank you, thank you, thank you all so much. Ray, let's model for folks here. Uh, so Ray, what is your thinking about the MLP? What could we do with the MLP to allow the model to learn and understand more?
I would say increase the number of layers and maybe increase the number of perceptrons.
I love it. That's it exactly, right? We can quite literally make the MLPs bigger. As a matter of fact, that use prior to this past summer, we thought that was going to be the path in order to get better and better models. So the name of the game was just make those MLPs bigger, add more stacks, the models get better and better. That's why we started to talk about bringing 3 Mile Island back online, for example, building more power plants, building more data centers, and finding ways to power the AI revolution because we thought that it was making the models bigger by making the MLPs bigger or by adding more stacks that the models would get better. But then something funny happened. We started to not get as much return for scaling up the models in size. But that is how we got to large language models, because large language models means it's trained on an immense amount of information and it's also big, many parameters. So multi-layer perceptrons, those are getting huge and there are more and more stacks. But did you all see GPT 4.5 when that was released? Remember, you may have even forgotten because we don't talk about it too much anymore. But GPT 4.5 came out, huge model. And yet, the biggest selling point for it was that its vibes were better. It was more emotionally intelligent, but it wasn't all that much better at programming or doing anything else. And it was really slow and really expensive. I'm betting that GPT 4.5, I'm betting that was GPT 5. I'm betting that that was the model that they thought was going to be the next big model. And they were testing it. That's why they never released it. We were on 4 for a long time because 5 just never got really good. So they scaled it up huge compute, huge amount of energy, and it had better vibes, and that was kind of it. So not a great return. So do the email multilayer perceptrons contain information or information disinformation? It's just learning. It's gonna it's gonna be information. It's gonna be correct information and incorrect information, right? It's gonna know uh, it's gonna be trained on what we wrote. So the models are trained in what's called a self-supervised fashion, and we'll probably touch on that in just a little bit. But the idea is that it's trained on any writings that we've produced. So that's the other way. So one way you can scale up the size of these things, but that has diminishing returns. Another way is that you can just train on more information. It used to be big news when the first models were trained on billions of tokens. Well, then we did hundreds of, tens of billions, hundreds of billions. Then we had trillion tokens. So that's enormous amount. The latest models are trained on upwards of 13 trillion tokens, an immense amount of information, and it's all information which is there. It's not labeled in any way because it'd be an impossible task to try to label it, but it's on blogs. And think of all the incorrect things you see on the internet. That's going to be there. But it's also trained on textbooks and on special curated data. It's trained on all of those things. So the tokens are coming from books, articles, blog posts, Reddit, other screeds that you may find online, synthesized textbooks, um, you know, uh, uh, captions of videos, pretty much all the text which is still accessible. Um, so let's go and Sanjana, let me go and take your question. Still a little confused between the attention and the MLP layer. Think of attention as allowing all tokens to communicate with one another. So the job of the attention is to allow each token to influence all the other tokens. MLP, what MLP does is, given that token embedding is in a new position, what else do you know about that position? Enrich that with the knowledge that it has. So when we moved King over, it was in a space that had to do with games, maybe winning and a move. And after the MLP, it got moved a little bit more, and now it's solidly next to checkers and winning, and a particular move in checkers, which comes after you move your piece across the board and you get more powers. So it got enriched with the MLP information. All right, Manish, you had suggested that one way to get the model to work better was to increase the token size. Exactly. So let's say that you've made the model bigger, better. So originally that token size was about 8,000 tokens. That's a couple of typewritten pages. And that's everything, right? It's everything that you put in plus all the words that it produces. It's that entire conversation. It's all got to fit in the context. That's why you run out of context length and you have to stop a conversation because it's run out of context. So one of the earliest things that happened was increasing that context length, because now the conversation can go on longer. We can also put information in there that's useful. So maybe you wanted to know about something that's more recent, for example, because these models, they're expensive to train. They're not continuously updated. That means it doesn't know about what's happened in May of 2025. So maybe you're asking about recent events, and so you load up some of the context with recent news articles, right? Or you're doing particular work in a particular specific area of research. You might upload a couple of papers that have to do with just that research. Yeah, maybe the MLP has stored information about your research area, but you wanted to know these two articles in depth. And remember, if we upload the articles here, those articles, all parts of those articles are going to influence everything that you talk about after that point. So that's the power of attention. You say something and you use it in a particular way, but you want it to be informed by all this research that came before explicitly. That's the way to do it. You don't try to hope that the MLP's learned enough about your research. No, you put it in context, because then you know that it's considering all those important things as you're doing the interaction. But in order to do that, you need a lot of context. And so context grew from 32 to 128 to even a million. So 1,000K, a million tokens. That's about 750,000 words. It's an immense amount. So you can put in multiple chapters, you can put in books. So now you can have a huge amount of context that you know the model will be taking into account as it's working through and answering your problem. So let me pause here. Joyce, I'll see if I can answer your question. Then I want to take other questions as well. How much weight is put on tokens in context versus tokens from the training data? So tokens in the training data are going to be learned by the MLP. It's going to be represented there, right? If it's trained really heavily, then it will get it very particularly right. But most of the time, think of it like a JPEG of knowledge, right? It's not a database, right? It's learned about the papers. Is it going to get the exact volume correct? Is it going to get all the numbers exactly correct? Maybe. Depends on how heavily it's been trained on it. But if it got trained on this one article one time, it's going to be approximately correct. Don't trust it to come up with the exact numbers, right? But if you put it into context, and attention is operating on it, then that full information from the paper is influencing what's going on. So I'm a big advocate of using that context well, and by putting things that are important in there, in there. So Thad, people used to talk about number of neurons to describe neural network models. Here's the interesting things. Yes, here you can talk about parameter counts. And that gives you an idea of the size of the model, but not necessarily the capability of the model. Because it turns out, yes, larger models could be more capable, but only if they had sufficient training and good enough training. So I bought a Mac. I bought a Mac laptop that was completely filled with memory. It's 128 gigabytes of shared memory. And I did that because I want to be able to run decently medium-sized models. So I can't run GPT-4o, but I can run Qwen 32 billion parameter, and that model performs as well as GPT-4. So not GPT-4o, but GPT-4, which took many, many racks of servers. But the training improvement and the care which taken with curating the data has resulted in much smaller models that you could run on a laptop, an extremely beefy laptop, but still they can run on a laptop that rival the frontier models of 18 months ago, or even almost a year ago. So curation of data, carefully curated training can get you much further, even though your model may not be as big or have as many layers. But you can also get very, very small language models, which can run even on much smaller memory. Even can run on edge devices, could run decent sized models, can run on your phone. The models know less about the world. They won't get things as precisely correct, but they understand multiple languages. They can do useful things for you. And here's the trick. All those models now have long context length. So if you wanted to get something exactly right, you know the model knows English and Mandarin and Arabic. Yeah, it knows all those languages, but it doesn't know about this particular thing. Great. Use that long context to populate the specific knowledge that you need, then ask your question. So, Sanjana, our initial token embeddings generally standard for different words in the English language. So the token encodings are kind of like builder's choice. And you have to choose them carefully to make sure that you can represent multilingual data sets well. And if you don't, then you kind of pay a price. It's not learned. Those token embeddings, I'm sorry, the token encodings are chosen. Everything else is learned. The token embeddings are learned, the positional encodings, attention weights, MLP, all that stuff is learned. But the token encodings are chosen before you start training. Dan, you were asking, yeah, actually, the answer is both better data and more data. And even the order in which you train is important as well. So curated training examples turn out to be very, very important. Other questions before we move on? Okay, so what if we break down tasks and steps and assign an LLM agent to each one? We're going to be talking about agents, absolutely. We're going to be seeing them here, as a matter of fact. And you're going to see that might work, absolutely, but it has to be a problem which can be broken down well. This works really well when you have tasks that have different components. You want somebody to be watching the progress of what's happening. Are you staying on track? You want another agent to actually be carrying out programming for you. You want to have another agent, and the communication between these is going to be extremely important. Okay. And so some tasks lend themselves to agentic approaches and some don't. All right. Other questions? All right. Thank you, Umang. Okay, Daniel.
Yeah, so I just want to make sure I understand correctly. So, is it possible that as you're adding more and more data, what's happening is you're getting a lot of conflicting information, and that conflicting information is messing with the statistical regularities that the model would pick up on, and so the training is not producing better results necessarily after a certain point because there's too much conflict in the data, right? I mean, there's too much noise to get to the
Mhm.
real answer, or
Mhm.
is it something just limiting, and there's just a point of diminishing returns where adding more doesn't really help for, again, statistical reasons rather than anything to do with the content of the information.
I I would say I would say that your idea is probably directionally correct, right? In that, um, uh, if you have conflicting information, you have to have enough context in order to make sense of why it's conflicting, right? Yes, it's learning the statistical regularities, but we are way beyond our understanding of what that statistical regularity looks like because it's so high dimensional. So that means, yes, it's learning statistical regularity, but it's really learning the distributional space. And that distributional space is far beyond, it's so high dimensional. We're now to the point where our original ideas of what it means don't hold anymore. So, for example, the model will learn hierarchical representations and subtle representations. And yes, it's using a statistical mechanism to do that, but we no longer get to talk about marginal distributions or conditional distributions. None of that holds for us to understand what those activations and what that representational space looks like anymore. So that's the only thing I would caution there is to say you would think it would sort of break down and it's understandable, but that would be reductionist because now we're talking about such a complex space. We don't get to map it down to our easy understanding. But broadly, I think that that's not bad. But I think that the task there is to be careful in the training. So think about when you're teaching someone in a class, you'll notice that I didn't start with, okay, I didn't start here with this graphic, right? I didn't say token encodings, token embeds. Now we're going to do attention. Now, I circled in, right? So I was giving you a framework with which to actually explain. And so you'd have something to then attach things to as we went more and more into detail. It turns out that's also important when you're training models to allow them to have framework. And so the things which might come later, which might be in conflict, can be understood. So you understand that, yes, you're going to have two different people that have very different viewpoints of the same kind of information, but there may be reasons for that, right? And so then having two totally different conclusions from the same set of data, um, at least may be understandable, right? At least may be understandable once you have enough of a rich enough understanding. So I think that uh, there's kind of a limit to what's written and to what can be learned from what's written. Uh, and we're about to see one way to go beyond that. Um, Now, Manish, you were asking, how does increasing the context size increase the number of parameters necessary? It doesn't increase the number of parameters, but increasing the context length increases the compute. So think about attention. Every token is going to be compared to every other token. And you're going to be doing a weighted average of every token of all the other tokens. This grows as big O n squared. So this is exponential. So that means the amount of compute needed to take this long of a context and to take every token and compare it to every other token gets huge. So that's a problem. Um, so it gets harder to compute, takes more time, but at the same time, it really greatly improves the work that the model is able to do. Attention is quite literally a weighted average. It's not just a statistical majority. It actually is a weighted average of the influence of each token embedding to every other token embedding. The original token encodings, not the encodings, but the embeddings are learned. So being trained on all this data, it's kind of random at first, but hey, king sort of ends up here, and then royal ends up here, crown, monarch. They all end up in about the same space because it solves the task of the learning task that it has. All right, and Daniel, did you have another follow-up?
Yeah, so just really quickly. So you were in response to my earlier question, you said, effectively you've given a lot of context, and the context helps disambiguate essentially different situational parameters that help the model understand what should come next. So my question then is, are we just talking about linguistic context, or does anybody
Mm.
train models with, I suppose, some sort of document level annotations that would tell you something about the conditions in which the document was created that the model could then learn? Or does it go the other way, right? Do we infer information about the conditions in which the document was created based on the linguistic distribution of tokens, I suppose?
Well, let's do this if we could. Daniel, I'm gonna finish up our conversation about the model architectures. Um, and then we're gonna do a quick exercise together so you can get a sense of what this training looks like. Um, and then I'll be able to answer your question. And then we're gonna take we'll take uh, a 5 minute break. And I'm going to ask you all to, we're going to do an exercise right before the break. So let's go ahead and go back to our model here. So I was saying that now we have 1 million tokens. That's dozens of chapters. Notice I say 1 hour of video. Those aren't words. We'll get back to that in a moment. There are models which can even do 10 million tokens. This requires immense compute, but it's possible. So now you're getting models with this immense amount of context length to work on. But here's something I haven't told you. Models, these are called native multimodal models, can take not only words, but images and audio and video. So models like GPT-4o, Gemini 2.5 Pro are native multimodal. So that means text and images can be put into tokens, which are then put into embeddings, and they learned all of this all at the same time. So the models have knowledge of and representations of images, audio, and video in addition to text. So now, yes, previously the model was only learning on what we'd written, right? What we'd written about the world. But now the models can learn about images and video and audio. So these are not things that we've produced. So now the models have ways of learning more directly about the world that are not mediated by our understanding. So these are broken down in many different ways where where it goes from image to token embedding. Some are simpler than others. The simplest is, but this is not how GPT-4o works, probably, is you take small squares. It actually is more complex than that now, but you do end up with an embedding for the image and actually different resolutions of the image as well all end up as embeddings. Same thing with audio and same thing with video. So it can take up a lot of space. This is why I say, hey, with 1 million tokens, it can do 1 hour of video based on a tokenization scheme. That's what Gemini Pro 2.5 can do, an hour of video based on its type of tokenization scheme. All right, but then, everything that we saw before works kind of the same way. You can put this in and you get response text out. All right. So let me pause for questions here, and then we're going to do a quick exercise so we can understand a little bit more about how the models are learning. What questions do you have? All right, so do you need to explore the entire trained token space, or can you subdivide into relevant and irrelevant tokens? So there are tricks that you can use to reduce the complexity, the computational and storage complexity, size requirements for attention. And it turns out this is actually key to get to the 1 million and 10 million token. And there are numerous approaches to this. Sparse attention. There are even very different types of approaches that are called state space machines. But yes, generally the idea is you attend more to certain tokens because they're closer or because they're strongly related than you do to others. So that is one way of doing that. And does the tokenization scheme affect the quality of context relationships? Sure does. So you remember before I said that earlier on, many of the models were like English centric, and that meant that the model could think better and reason better against English text than it could against Arabic. Umang, you once had a statistic for how many tokens your name took in Hindi. What was that? Can you remind me?
Yeah, so in English it was just I think 2 tokens, but in Hindi it was 4. It was twice as much, and then I think I tried it in Arabic and it was 6.
Yeah.
So it really does matter.
So think about it. And to get Umang's name previously, it just had to combine, it had to link 2 different tokens. But to do it in Arabic, it would have to link, 6. So that's different tokens that sort of need to be put, moved to about the right part of the space. It's a lot of work to do just to represent Umang's name and for him to be seen as like an individual that has these different properties. So thinking literally is harder if your tokenization scheme is no good. All right, let's do an example of learning. And yes, Sanjana, sometimes tokenizers are shared, but once you have a tokenization scheme, you're kind of stuck with it. So that's why you gotta have to make a good choice earlier on. Let's go ahead and do we're gonna do uh, a task here. This is gonna be from Zora Neale Hurston, Their Eyes Were Watching God. I'm gonna flash this in front of you, and I'd like for you to be ready to type into your chat. And what I want you to do is I want you to type into the very first word that comes to mind. So what I'm doing here is I'm going to give you the sentence, but I'm going to leave off that last word, and I want you to just type out immediately that first word. And I want you to commit to this because I want wrong answers because I want to be probing you early on in your processing, right? So think of a word first, then commit to it. Just think of the word, put it in. If it's stupid, great. You're going to be revealing something, right? So are you ready? Okay. I'm going to flash the word. Think of the very first word that comes to mind and type this in. So this is the contract we have. You're going to type in that first stupid word that you thought of, okay? Here we go. Ships at a distance have every man's wish on. This is really interesting. So I'm noticing all of these are nouns. So they're all nouns. Um, how did you all know that these needed to be nouns? Okay, yeah, so it could be it was on something. So if you reflect on this, you might say, "Oh, I know that it was the object of a prepositional phrase, therefore it must be a noun." Yeah, you kind of knew this, right? You'd represented that that's what belonged there. And if you thought about it, you might be able to come up with the rule for it. So Sanjana, Daniel, exactly. And Manish, right, your intuition, you kind of have learned the rules of the language. So you learn the rules of the language, let's say it could be a noun. The answer is indeed a noun. So to even get close to the answer, you had to know that it was a noun. Almost all the words that you came up with had to do with being at sea or a ship. Had to do with these words, ship's distance. So how did you know? How did you know that a ship had a mast? Well, you've been exposed to it. You had to know the semantics of all the other words in order for you to be in the neighborhood of what kinds of nouns you might choose, right? So horizon, mast, gold, all of those, water, absolutely. Those are all nouns and they all have to do with the semantics here. But it turns out that some parts of the sentence are more important than others. Ships at a distance have every man's wish on. So you start putting those together, it's like it's got to be somewhere on the ship. So now that influences which of those nouns having to do with being at sea matter and which one you might choose. So I have two words now. Ships at a distance have every man's wish on deck. Ships at a distance have every man's wish on board. Okay. How many people go ahead and vote. Put into the text chat which word you like better. Do you like on deck better or on board? Go ahead and type what your preference is. Okay, Ida, can I ask you, why did you like on board better? And you can just unmute and speak if that's all right. So
Yeah,
Ida, why
that's
do you
okay.
like? Yeah.
Um, I don't know. I think it's just like when you say it, and I think part of that's intuition because of what we've learned in the past. I think it just like flows better.
It does, doesn't it? It's metaphoric, right? We're not saying it's on the deck. Is the wish on the deck? Both feet planted solidly on the deck. No, it's like they're on board. They're carried. The wishes are carried. Yeah. Excellent. So think about all the different things you must learn in order to get the correct word, which is on board. You have to know parts of speech, rules of the language, semantics of all the words, which words should influence more. This is the attention weights. And finally, even style of writing, concrete versus metaphorical writing. Zora Neale Hurston, great writer, absolutely talking about ships at a distance having every man's wish on board. So, this is what you can learn through this, what's called self-supervised task. Leave out a word, use the other words preceding it, and this is called causal language modeling, using all the words preceding it to guess what that missing word is. That's called self-supervised learning. That's how these models learn. And remember, the models produce a probability distribution. So the model may produce on deck, but the number two, as the highest probability, but the next highest probability could have been on board. And so you can actually train and say, oh, you were close, but not exactly right. So then you use what's called back propagation to actually train all those parameters of the models. And so the model gets better and better at getting closer to what the words actually are. That's how the models are trained. That's how the extremely large models were trained. It's extremely expensive to do so computationally, but that's exactly what's going on. But this is how you can learn even subtle things like styles of writing using that. Nothing's labeled. We didn't do anything other than leave out a word and have the model try to guess what the correct word that was there. How do you learn on images? Leave out part of the image. How do you learn on video? Block out some of the video sort of over time and across a frame. blobs. So that's the way for the model to learn, not just on words that we have written, but on the world as it has been presented by the video and images that are given directly to it. All right. Other questions about how the models learn? All right. So we've talked about how these models could get better. We've talked about how we went from the smaller model to a bigger model. So that's part of it. You can make the models bigger. You can scale the size. You can scale the training. And so the models are trained on much more information as well. But here's one thing that we're going to be talking about next. There's one more kind of scaling that we're going to be able to talk about where the model can get better without increasing its size and without increasing its training. And we're going to talk about that right after the break. So let's go ahead and let's come back right at 15 past the hour. We're going to give ourselves 6 minutes just for a bio break. But I want you to be thinking about two things. Two things. One, I want you to be thinking about how else we might scale this model. And I'll give you a hint. Think about what I said previously about tokens. That is, you produce tokens that it's compute. So production of tokens is compute. So think about that. I want you to think about how you can make models better, not by scaling the size or by scaling the training, but by scaling something else. And two, we're going to start using these models, and I want you to be thinking about a research problem or some suggestion you can give me for a problem that we can solve. Um, and actually, no, I really better do this before the break. So let me take suggestions as you're taking a break. Type into chat a question that you have that you might want to have a research assistant do some work for you on. Okay, and this could be anything. You're interested in doing some research, you want to learn about something you might want to buy, could be anything. So, for example, I was asking the other day about recent advancements in multimodal AI models. So think about something you want to learn something more about that if you could hire a research assistant to pay them to do, that you could have them do. So put that in the chat, but let's go and come back in 5 minutes at 15 past the hour, right? But be thinking about a problem you want a research assistant to solve, put that into chat. All right, I will see you all in 5 minutes. Welcome back, everyone. So, thank you for your suggestions. Some really good research questions there. Let's go back to the first question that I posed. Can someone give me some ideas of how I can improve the performance of a model without increasing the size? What are some ideas that people have of how I can produce better better results? Tokenize on phrases or n-grams. Okay. So this is sort of one way of sort of like collapsing down the information, maybe. But remember, we do have other ways of creating longer and longer context lengths. So possibility, but may not just improve them. It could possibly improve the model, but I want a quick fix. I want a fix right now of how I can make this model produce better output than it did before. Yeah, better performance in terms of accuracy, better responses, more thought out. But yeah, definitely more accurate responses. That's what I'm going after. So one way is prompt engineering, being careful about how you ask, absolutely. So you could train the model further. You might be able to make some architectural changes, but what if I'm not allowing any additional training? Because remember, we tried that. We did a ton of extra training, and we came up with a model that had better vibes, right? We made a model which was bigger. And so fine-tuning, that's a possibility. But again, that's sort of training the model. We want to do something that isn't necessarily having to do with training. So let's think about this. Remember what I was saying before was that when you produce tokens, the model is computing. If we have the model do more compute, then the model can do a better job of solving problems. That means we need to find a way for the model to be able to produce more tokens before it answers. So, have you ever taught or have you ever been a student in a class? Actually, no, we do this all the time. Somebody asks you a question and you're like, okay, I know the answer. I'm going to start saying, you may not know exactly what the answer is going to be, but you begin responding immediately. This is how the models operate right now. You put in the context, you immediately get a token in response. It's already starting down the path of providing that answer to you. But we know sometimes when we're on the way to answering something, we actually don't know exactly what we're going to say. There are other times, though, when we pause and we say, let me think about this for a little bit. We might have an internal monologue to sort of think through what the question was, reflect on what we know about the question before we start trying to answer, and maybe even to try out some answers, but then to see if they actually hold water before we respond. This is called thinking, it's called reasoning, and allowing the models to reason before they respond turned out to be a remarkably powerful way to improve the performance of the models without changing a whole lot. So the first way of doing this is something just called chain of thought. And that is say to the model, think through, tell me your reasoning before answering. And that works okay. Even better is to provide some additional training to the model on how to think. And actually saying, okay, before you respond, emit a thinking token and then consider in the following ways how to respond, and then say end thinking and then respond. It looks like this. You have some context and it does thinking, and there's reasoning text, and then there is response text. So that's a way for the model to actually immediately respond better because it's actually gone through and thought to think before it actually responds. And Faisal, in week one distillation, yeah, it turns out that even smaller models can get much better and can actually match some of the larger non-thinking models just by training them on types of reasoning. So that's been the latest revolution, especially since January of this year, is reasoning models. And that's the models having the ability to think before actually responding. And so let's go ahead and take a look at what this looks like in practice. Let's see if that's still thinking there. I'm glad I kicked that off earlier. I'll take a look at that in just one moment. Let's go and go to a thinking model here. So the O1 model, or O4, is fast and it's a thinking model. So I'm going to say, let's see if we have something which is in here, some of the examples that you all have. Um, uh, let's go and take one of the how might screen time affect teen mental health? All right, now this is a thinking model. So we're going to give it, you're going to notice before it responds, it should see it's thinking. So it's not immediately responding. Here's a structured look at how different aspects of screen time can influence adolescent mental health. So in the O4 model, sadly, it hides it from you what it was thinking. There are other models where we're going to be able to see what it's doing. But this is actually a pretty well-considered response. Negative associations, potential benefits. So before it started its response, it thought and produced probably a couple of pages of thinking before it responded. So this is the difference. This is the kind of response you can get out of, and O4 is not a huge model. It's actually kind of small, but it produced a really good response because it could think beforehand. So thinking models where there can reasoning before they respond to you can result in much better responses. So how well do you suppose that this model right here would be able to answer questions about something in the news last week? What do you think? How well could a model, say this model right here, running exactly the way that you're saying? Yeah, not at all, right? Because the training for this actually would have ended months ago, if not longer. So it's not going to know. So if somebody asks you about an event last week that you haven't heard about yet, what's the first thing you all do? Let's say you're doing it, swapping text messages, right? So you have a little bit of latency there, so you have some time. Somebody says, yeah, and what about? What do you all do? You Google it, right? So you look up to see what's going on with it, then you can respond. So it turns out another way to augment the models is to allow them to use tools. So whenever the model is asked for something more recent, it actually can look it up and it makes a tool call to Google or to something else. Um, if you're asking it about something that might require the calculation of certain numbers, it might write computer code. Instead of trying to directly reason through that, which is not very good at, it writes a computer program to actually do the math to then answer the question. And that's what this looks like. This is tool use combined with thinking. So here are some tools. Internet search, code interpreter, might have a file tool where it goes and looks things up, might have an image tool where it kind of goes to find things, long-term memory, custom tools. All those things are possible. And this is what it looks like. So it produces, it calls a tool at this point. And so it might do an image tool. And then after that, it might do some code interpreter to write some computer code. And then it might go ahead and do an internet search here as well before it tries to respond to you. And then it responds to text, responds in text. So this model is, this is exactly what the O3 model is doing. So we're going to open up ChatGPT. and we're going to go to O3 model. This model uses advanced reasoning, and it also uses tools. Good question about long-term memory. I'll talk about that maybe during the break if I could. What is exactly happening differently from the usual process when the model thinks? Nothing. So all that's happening is it's making more round trips. It's producing more tokens, but the tokens it's producing look a little and they sound a little bit different. So when thinking, it's going to say, okay, I've been asked to do the following. I've been asked to solve this problem. What do I know about this problem? Here's a possible solution. Does that work? No, let me try again. So it literally is producing tokens just like it did before, full round trip, autoregressive, attention, MLP, all of that. But remember, token production is compute. Token production, which is in the service of solving a problem, is useful compute. So long as you are producing tokens in a way that's related to and moving you towards a solution, you're doing useful compute with your models. That's called thinking. When you get close enough, it says end thinking, and then you give your response. So that's what's going on. Which version is better, O4 or O3? Well, O3 is they're both tool users, but O3 we've not seen the full version of O4 yet. um, O3 is about 200 billion parameters. It's a heavy tool users. It's been trained heavily on using tool use. Um, So O4 Mini and O4 Mini High are faster. They're a lot faster, but they don't give as good responses as O3 currently right now. But probably when we see the full O4, it'll be supposedly, it should be much, much better. Manishi asked, how do you determine the optimal amount of chain of thought thinking? That's a really good question. We're going to be looking at the O3 model in just a moment, and that one is heavily trained through what's called reinforcement learning to use tools and to think. So if you ask it a really simple question that has like an immediate answer, it might immediately respond, but it's just as likely to overthink. So that's a problem with the models. You've got to know which model to use for it to ask it, to think or to not think. That's one of the things we're trying to do with the GPT-5 and with the Claude series of models to make these hybrid models that themselves can determine, does this require more thought? If so, I'm going to be doing more thinking and using more tools, or is this really simple question that I can answer immediately? So I think that's what a lot of the companies are working on right now to give a single model interface that knows when it needs to think deeply or not think deeply about a response. All right, let's go and try out our O3 model. So we're using the O3 model right here. And what were some of the questions you all had? Uh, okay, let's see. Okay, I'm going to say give me a list of best of. Here's this. What's the best Windows-based laptop to run LLM like Quen that's not too expensive? So we're going to put this in. Oh, you're giving feedback on a new version of ChatGPT. I've never seen this. That's fascinating. So it's now doing A/B testing of one of the new O3 models. Oh, and it's not showing me the thinking anymore. That's annoying. No, it is showing the thinking. The user is asking for a Windows-based laptop to run a large language model. I'm going to search for the latest laptops. So it's saying I'm going to use these tools. I'm going to consider the new laptops. So now it's thinking and you see it's searching. So you're watching it think and search and use tools. So think how fundamentally different this is. It's always running the same way. It's the same transformer architecture, but now it's producing the thinking tokens and it's also writing queries that are then being run. Then you just add that back into the context and continue running. Does a web search, puts it in the context, and then continuing. It's going pretty darn deep. While this is running, what questions do you have so far about this? The compute factor, it depends. Does using external tools like accessing the internet? I mean, Google search is pretty efficient. Writing code takes a little bit more, but it's a lot better than trying to have the model just reason its way through something that could be much more easily done just using a simple computer program that it could write. So here we're seeing response 1 is still working, response 2 is here. So it thought for a minute 32 seconds, this thought for a minute 40 seconds. So you can see it's given a really fully considered response here, response 1, response 2. I'll leave this up and I'll check it out a little bit more so notice here it's a void, only 6 gigabytes VRAM. Hardware to insist on. It's even comparing the models and what can run where. So far, the one on the right is really pretty good. So think about the considered response that you're getting here when you have something which is both reasoning and a tool user. This is an example of a simple agent model. You give it something and it's actually running off and doing things in a very tight kind of a loop. It's not really a separate agent, it's a single agent, but it has agentic properties. It's able to come up with its own tasks. I need to look this up. I'm going to reason against this. Now I need to look up something else and then return to you the results. So if your context length is long enough, then you don't need to have multiple agents necessarily because this was a unitary task. Answer this question. If I had said, now compare this to other types of approaches or compare this to historical compute, then we might have wanted to have a more agentic to could do more, but this is easily done within the single context. Is it similar pre-priming context? Kind of. Remember, in context, everything gets considered, right? So everything that it found in its research and everything that it wrote gets considered. So when it came up with this TLDR, too long didn't read, it considered all of that. So, all right. So we've talked now about the basic transformer architecture. You've now seen the O3 model running. Let's go and take a look at another kind of an agent approach, and this is called deep research. So here I'm running the 4.0 model, not a thinking model. I asked it to do something, but when I did this, I clicked on deep research. This let it know that I'm actually asking 4.0 to kick off a totally separate process. 4.0 is going to be calling a different model. It's going to be calling the O3 model multiple times to solve a research question. What's the research question? How secure is my health data on wearable devices or telemedicine platforms? All right. So the first thing it does when you do deep research is ask you clarifying questions. Then you get to answer very telegraphically at what you want. And then it's going to tell you what it's going to do. So it tells you what it's going to do here. And then it did research for 7 minutes and 19 seconds. It searched 117 resources. So it's doing a lot of research. Deep research is the calling of the O3 agent repeatedly until it has what it considers to be a full report. And here it produced the full report. Security of healthcare data on wearable devices. This is a pretty extensive report. Has the intro, storage options, data transmission security, third-party access, data sharing, legal and regulatory frameworks. So you can see this is reporting a lot more than O3 did on its own. Known vulnerability, best practices. So this is what deep research produces. So an extensive report using O3 as an agent. Here's the nice thing. When you are actually doing lookups and you're pulling all this information in, now instead of hallucinations where it is, I mean, all the model ever does is hallucinate, produce the next probable output, right? But now you're getting and putting directly into context lookups, results of code, results of tools during their work. That makes responses much more likely to be coming just from what it produced. Why would you have something that's not factually correct when you have the facts right here? They've been loaded. So reasoning models tend to produce fewer of those types of hallucinations. It tends to get things wrong less because it's always checking for consistency. It turns out O3 model in particular, when it first came out, hallucinated in a different way, which is it was so heavily trained to use tools, to use tools frequently, often, that sometimes it would say it had used the tool when it hadn't. This is called reward hacking because this was trained in what's called reinforcement learning. That seems to have reduced now already. But whenever you have models that are using tools and are thinking, it tends to seriously, seriously drop the sharing of incorrect information. All right, I would like to take, let's see, we have 136 here. I'm going to suggest that we try some breakout rooms so you can get some hands-on experience with this deep research. So, Umang, are you still around? Let's see if I can get to this real quickly.
Yep.
Great. I would love to share that link to that document. I and do you know what document I'm talking about?
The
The
breakout
breakout.
room document?
Yeah, yeah.
Yeah, let me get my hands on that.
Okay, great. What I'm going to do is I'm going to set up breakout rooms real quickly. I'm going to stop sharing. We're going to share the breakout room document, and what I'd like for folks to do, I'm going to be creating breakout rooms. I'd like for you to go into the breakout rooms and actually work on a problem together for about 5 minutes. Um, it's gonna, well, I might do, I'm gonna make it 10 uh, minutes. How much? 37. I'm gonna make it, let's see, we have 40, 55. I'm gonna make it 10 minutes. We have a bit of a problem here because usually the deep research takes. So we're gonna give it a shot. I'm gonna randomly assign you uh, 2 to 3 participants a room. Actually, let me go to assign manually. I'm going to let's see, and I'm going to randomly assign and try to get you into a decent sized room. So the document should be shared in. So go and open up that breakout room doc. So let me know if you have any trouble if opening that breakout room doc. But what I'm going to ask you to do is to share your video upon entering the room because it's much easier to work together when you're sharing your video. Select a volunteer to share their screen and carry out the model interactions for everyone to see. I want you to actively make notes down below. You'll actually see room 1, room 2, room 3, so I can actually monitor what's going on. And here's the task. Choose a topic that you would like to have research, just like we were just doing, and then copy the prompt in the space below. Go ahead and run it. I'm going to ask for somebody to try this using deep research in GPT-4 and somebody to use Perplexity. And I'd like for you to take a look at what's happening, take a look at it, and then to come back and be ready to report in the last few minutes of the class. All right, is everyone ready to jump into a room? Any final questions before we hop off into the rooms? And we're going to be there for let's see, we're going to be in the room for um, we're going to do 15 minutes for the room. Give us just a few minutes. All right, we all ready?
I think there's a question, Faisal.
Yes, go ahead.
A quick question. Should we create our own prompt, or did you say you were going to give me the
No,
give us the
you
prompt?
you can discuss in the
Okay.
room what prompt you'd like
Thank you.
to what prompt you'd have that absolutely. All right, I'm going to open up the room, so people are going to get tossed into them. I will be roaming around to see if you have any questions as you go in. Uh, let's see. I've got to assign the rooms, don't I? Okay, so here we go. I'm just going to be. Give me a quick moment, and I'll finish assigning. All right. See you all in just a little bit. All right, Umang.
How are you doing?
Doing all right, thank you.
Yeah.
I only do breakout rooms usually during AI summer, so I get rusty.
Yeah. Give me a second. My camera is dirty.
Looks like good conversations are going on. Would you mind going in to room 5? It looks like, oh, Thad is finally joining there. Well, they might have enough. They just have 3 people, though. Would you mind popping into
Sure.
room 5? Okay, yeah. And is anybody stuck in here, or anybody need to be moved in? Hey Siri, add fruit to Florida shopping.
I didn't find a Florida shopping list. Do you want to create one?
No.
I will not then.
Alexa, add fruit to Florida shopping list.
You'll need to unlock your iPhone first.
Welcome back, everyone. Welcome back. All right. So let me go ahead and ask. Tell me about the pattern that the model was following. How was it thinking? What was it doing when it was trying to solve the problem of of the prompt that you gave it?
Ours was checking everywhere on the internet for resources and scientific articles and things like that.
So it went out and searched. Did anything happen before it started to do the search? What was one of the first things it did?
Well,
I
for
don't
us, it just, oh, I'm sorry, please continue.
go ahead.
I was just gonna say, for us, it just, it came up and said beginning to answer your question or something to that effect. And then after a couple minutes of that, it just went straight to looking at websites.
Oh, okay. So, yeah. So
It also asks questions, some relevant questions for the
right.
research.
So deep research first asked you questions you had to answer, and then it sort of told you what it was going to be doing. Think about the utility of that, right? Asking questions, getting clarifying information, then restating what it's going to be doing. It's not just restating what it's going to be doing for no reason. It actually is it's putting that into the context of saying, hey, this is what I'm going to be doing. And then it's going to remember what it's doing because now that's in the context. It's been generated. It's going to guide its actions from that point forward. Tell me a little bit about the resources. I noticed some folks mentioning it seems to be going to the websites rather than to the actual documents. How many people saw it actually go to PDFs or to source documents? Yeah, not a whole lot. Why do you suppose that is? Daniel, why do you suppose that is? Go ahead.
Well, I was gonna say at one point, it looked like it was, so we asked a question about linguistics, corpus linguistics, and at one point it looked like it actually went to a web interface for a corpus, like it was doing some original research at the corpus, but then it that didn't end up in the list of sources. So it looks like it went there and tried something out and then didn't use that information.
Mm-hmm. So this is actually something which is evolving right now. One of the things that the deep research and other models that are doing things like that are doing is developing ways to actually access information as humans access that information. So if it can't download it directly, can it form a search query that it would actually type into a human-like interface in order to get that information? This is a challenge, though. What are the legalities around an assistant, a bot assistant, accessing information on your behalf? It's not settled. So, one way to make sure that it's using information that you want it to use is to upload that information into the context even before you start the deep research. That's one way, because if it's in that context, remember you can load it into context and it will definitely be using that as it's moving forward. This is a fast developing area. So as the technology progresses and the legalities become clearer, what you'll likely find is, hey, I may come back and ask you for access to what you have access to, your credentials that I won't be aware of. But if you will get me in, then I will do the research on your behalf to get access to everything that otherwise I would not. But right now, it's much more public facing. I'd like to thank you all very much. We went all the way up to the end of our time. Thank you very much for all of your questions and your suggestions. Go ahead and stick around if you'd like to for our office hours, which are going to run from now until the top of the hour. But be sure we're going to be back on Wednesday. Wednesday, we're going to be talking more about agents and how agents might actually be broken up further to do even more specifically defined work. And Professor Bell is going to be talking about that. Then we'll continue our conversation and talk more about multimodal models, native multimodal models, and how they work. So stick around if you have additional questions. Otherwise, see you on Wednesday. Thank you, Keith. Thanks, Daniel. Thanks, Renee. Thank you, Lily. Thank you, Sanjana. Thank you, Joyous. All right, folks, what questions do you have?
I had a question, Jesse. So like I think we started like giving the prompt to it like 15 minutes ago and it's still running. So my
Yeah.
question is how does it determine like how much, additional tokens to generate before like actual answering your question?
So that's also an area. There are hybrid models where you can actually, well, you'll notice that when you look at the list of models, the O4 mini model has O4 mini, and if you have the Pro version, it has what it's called O4 mini high. The high refers to the number of thinking tokens it's allotted before it must respond. So it knows it only has this many thinking tokens. Sometimes it'll end earlier. When the model determines that it has enough to produce a good answer, assessing what it has, have I carried out my research program here, where at least I've gotten some information on all the main points that I brought up. If that's the case, stop the thinking and begin just answering, right? It doesn't know exactly what the answer is, but it knows that it's at least has information that's relevant to all the things that were brought up before. And so it's okay, at this point, now I can begin my response. And at that point, it just begins its regular response based on this enriched context that it has now created. Um, you can set different values for some models so they have more space, but whether or not they actually use it is up to the particular problem. Great. Other questions?
Quick question,
Hi,
Jess. Sorry, go ahead. Someone before.
uh, yeah, Jesse, I had a question on the reasoning models. You said the O3 and all these reasoning models, they use heavy, I think you said reinforcement learning,
In their
um,
training, yes, correct.
in their training, but all the models use, I would think, a decent amount of reinforcement learning, like at least RLHF, right? So like, what's the difference?
So, so what we're talking about here is reinforcement learning, and there are lots of, it's not all of reinforcement learning. So we call it reinforcement learning, but actually what's happening is we're using very specific parts. So what we talked about before when we had the task of guess the next word in the phrase, that's supervised fine tuning. So that is, it's pretty clear. You got to guess what that next word is. How far off are you? Well, what's the probability of the real token versus the token, what's that probability of the token that was produced? Is it low probability? Is it high probability? I'm sorry, the correct answer. So what's the token value of the correct answer? With reinforcement learning, you have various types of reward functions. And the earliest types of reward, the RLHF or RLAI that you were mentioning, Mohsen, and good to see you again, by the way, is um, are you being kind in your response? Are you being helpful? You're not being harmful. So those are general sort of scored responses, and the model is broadly trained on those types of activities. Almost every model, you're right, has some type of that training. For reasoning, you can use both supervised fine tuning and you can use reinforcement learning, but almost always a little bit of both. So the larger models tend to have some training on supervised training of here's a problem, here's the reasoning you should use. That's supervised fine tuning. And that's sort of the cold start problem. If it has never produced anything that's reasoning like that, gets it starting. Then you move to reinforcement learning because then it's more like, was your reasoning good? Was your reasoning good sounding? Was it all in English or did you slip into some other language or slip into a non-language, right? Because that happens too. So reinforcement learning sort of aligns it. And so when it has that thinking token, it's responding in a particular way until it reaches the end thinking token, in which case it needs to respond as usual. You're not using all of reinforcement learning. It might be group policy optimization. It might be lots of different ways, but you're shaping the model, aligning the model versus saying respond like this. So that's why reinforcement learning. Other questions? Yeah, Lily, go ahead.
Yeah, so again, about the privacy of data. This is one concern that I am stuck with. So I have two projects, one of them, but both are the same basic image recognitions. One, brain images to recognize the disease, which is exactly the same, to another project. Both are based on grants. The other one is we have images from the transportation department for MRI grant, where I cannot use this publicly. Have you seen some type of research where ChatGPT, you can trust it to upload those images and you can guarantee that those images, or there's a policy, specific policy, not to put me in any bad situation where I can use either based on patent or based on privacy data from the Department of Transportation, for example?
So here, this is the interface for something called LM Studio. And Monk, did we talk about that a little bit on Wednesday?
Yeah, we did. Yeah.
Yep. So LM Studio is one way where everything is completely private, right? It's like it's only running on your laptop. So that's one possibility. Just run something locally. Now, if you have paid versions, like I have some video I'm going to be able to upload to Google Gemini 2.5 Pro because I have the AI paid account, and so I know they won't train on the data, and the permissions I have allow me to do that. For extremely sensitive stuff, though, I have to run it completely locally. So you run something like LM Studio.
Okay, thank you.
Absolutely. Faisal, you had a question?
Oh, me?
Yeah, I thought you were starting to ask.
Yeah. My question was similar to the last question. So when we are doing this, the deep research option under ChatGPT, it's often using this Wikipedia or news article as sources.
Yeah.
And to prevent it from doing so, one option might be I could tell it that please do not use non-academic sources. The other option I was wondering, would it do even better work if we use LM Studio kind of things where I'm training an AI just to grab scholarly sources or search like a human would search in different sources?
Well, think about tools, right? So one possibility is you could have a custom tool and you'd say only use this tool, and the tool would only go after specific resources. As a step towards that, yes, you can within deep research before you actually kick it off say the following are allowable, resources, or you could say that actually in that prompt. Because remember, deep research in particular is going to be shoving everything over to O3. So you want to have that right there in the prompt where you're asking, say, these are the allowable sources and do not use the following. That will guide it. It won't be 100%, but that will certainly guide it. If you want to have the model actually, if you want to guide it more closely, then and you don't need to have like a full report, maybe you call on O3 directly. And in O3, you just put there and you say, here are the I've uploaded all the articles I want you to use. If you need to look up things, here are the usable resources. Do not use the following. And then you can iterate with it, because then you get an answer and you say, you used another source, retry. So that's different from deep research, which is just going off and doing its thing. O3 interacting directly with, especially if you want tight control, that's one way to do it. Another way is, now that the reasoning models are getting really good, even in smaller packages, is you're right, you could run it within LM Studio. LM Studio now has the ability to call tools. It requires some extra coding right now, but you could run LM Studio, have it running a tool which actually has access to your internal resources, for example, and it can preferentially call those to get that, that preferred information or data from wherever it is. Yes, Daniel.
Thank you.
Absolutely, Faisal.
Yeah, so earlier I asked a little bit about if there's any sort of document level annotation that goes into training. And you said, maybe we get to that. So I just want to stick around and see if you can expand on that a little.
So think about the type of training that that it does. It takes some amount of text and then does causal learning, meaning you cut it off at some point and you say, all right, now guess the missing word. You can actually train it, and so it would always have the title of the article and maybe a few paragraphs before, or you could just grab from the middle, or so it really depends on the choices you want to make during training. And closed sourced models, we have no idea. Fully open models, they actually share what and how they trained, and then you can know what they did. Um, so that's the problem with closed source models or open source models that aren't completely open. Like they don't tell you what they trained on or any instructions that they gave during training. So you know what the architecture is, you know what the weights are, you get to use them, but you don't know what's trained on. Fully open models share everything about it. Here's the data we trained on, here's the algorithm we use for training. Then you can know. So for large part, the answer is we don't know because we don't know what they trained on. But there's no architectural change which is necessary. It all has to do with how you curate the data for the training.
Yeah. So when I ask ChatGPT or whatever to respond to a query, but to do so with a specific tone, right?
Mhm.
So what's happening? So again, I kind of assume that it must be the case that there's some portion of the training data that it, like if I say, answer in a really conversational tone. So somehow ChatGPT understands some portion of the training that went into this was conversational, and maybe
Or,
through okay,
or
yeah, go
let
ahead.
me pause you just for a minute, just because it's not necessary for it to be done that way. Um, so it could be kind of like the model just happened to be exposed to different kinds of writing. I'm not telling you that I'm like speaking really conversationally right now.
Mhm.
I'm not. I'm not telling you I'm being conversational, but
But it figures it out.
like if it's going to guess the next word I'm going to say, it's going to help if it has this representation that, hey, he's talking a different way right now. So that's up here, right? That is okay. Here's this learned association that answer sounds different from models from hierarchical representations, regardless of whether actually labeled. Speaking style is actually innate in the context, and the formality of it is part of the context, even if never explicitly stated. Okay. Now, for
Yeah.
that part of the response, it says, that sounds different, right? So now it has a representation. Now, at some point, somebody's going to say, I don't want a conversational answer. And then it's like, oh, all these things that I labeled before, that word is conversational.
Because you've said that in your content.
Because at some point somebody said it, so it doesn't have to have it doesn't have to have a ton of training on formal versus not, but it is, that's that context, that word fits really well with that representation that I was using to describe this thing before. So you can see how it builds on these representations. That's what makes it such a powerful general purpose learner. It learns the representations and it learns the relationships between the representations, and it learns the names or the ideas behind the representations. So
So I
without
have
ever
about 75 follow-up questions, but I don't want to take all the office hours time. So let
No, that's
me
quite all right. But I hope that sort
turn
of
things
gets you in
over.
that right direction, right? Then you get all that for free. It's like conversational, like not formal, like what you might hear on a street corner. Okay, that's here in the space. Here are all the things around it. Manish.
Yeah, this is actually following up on Daniel's question, but say for like the word conversational, like when you say representation, you're talking about like the vector embedding that was in like the semantic space that's conceptualizing the concept which then relates to what it means.
It is partly there, and it's also partly in the activations broadly across. We didn't talk about that, but the model has preferred features that it uses when it is actually processing text. But that is a function not of the weights, but of the activation space. It's a whole other topic, but it has preferred ways of representing the world. And those preferred ways tend to get used and reused. But yes, that then shows up in what ends up in those embedding spaces. But yes, the embedding space is, it gets informed by everything else. And when I was talking, like informally, you know what I mean. When I was talking informally, all those words together are influencing all the other words, and it's moving all those vectors, seasoning them just a little bit with informality. So, yeah, it's that word, but it also has in that vector, it's moved towards the direction of informality.
I see. And then my other question was regarding to tokens. So like you said, like just for simplicity, that like a token would be like a single word, but like what would happen if a token was like a single letter or like a sentence? Like how would that affect the model?
Well, there are different types of encoding. So there are byte level encoding. Sometimes you have a mixture of both. Maybe you have like words and subwords. We also have some byte level encodings for good measure, so you can at least represent things that have never occurred before, right? Um, and
Yeah.
that's sort of part of the mix. So go ahead, Uman.
Yeah, I just kind of you said what if it was a single like character? So this is what I really saw when I started working with a model that hadn't seen like a different language before, especially a language that isn't in, just Latin text. It's more like Hindi, some just completely different script. So in a computer, that is being represented in like some Unicode character. So the second I started asking this model that had like seen very little training on Hindi before, it started like literally generating one token per Unicode character. So my name, instead of being two tokens in English, ended up becoming 5 tokens in Hindi, or I think a little bit more because there's stuff in there too. So it just made the actual impact of that, obviously, it's going to be harder for it to really work with it because it really doesn't have good representations of these individual characters or just words as a whole when they're combined, but also just computationally more expensive as well.
And if you think about it, all those tokens have to inform one another through the attention mechanism to sort of be bound together. They all sort of migrate to about the same part of the space. All those 5 tokens sort of have to end up there. Now together they represent that name or that meaning. Hey, Umang, I'm gonna have to hop off right at 2:30 if you can continue to answer questions. I just have a competing meeting that just showed up from the state of Tennessee, so I'll hop onto that. But Thad, you had a question about how are thinking tokens different from response tokens? They're really not. It's just that it emits a thinking token and then has all the stuff after that. So it knows if it has seen a thinking token but has not yet seen an end thinking token, it needs to act in the following way. And then when it's done, it emits an end thinking token. Now it has, yeah, thinking token, end thinking, but now it knows that it needs to respond in a different way because now it's seen an end thinking token. It's time to just respond for the user.
Okay, good. Jesse also had a question when you're talking about formal and informal.
Yeah.
It made me think about scientific, which is very formal, and artistic, which is very creative and often non-literal on purpose. Do you think are there like thousands or millions of these spaces, or do you think those two spaces would be similar?
When we get to that level of discourse, I like to start talking about the activation space of the models. I like to talk about the feature space because it's what the model has learned, right? So one really interesting independent study done by a senior who's actually one of his majors is literature, was to look at small and medium language models to see how good of a job they could do to represent different styles of writing and what the activation space looked like for those. The very smallest models, it would call anything that, sounded a little bit older English, it just called it all Shakespeare. Like it had a Shakespeare feature and it just turned on that that Shakespeare feature, and that's how it represented all that language. But then with the larger models, it had other features for different styles of writing and different authors that would begin to represent. So it had a finer and more subtle representation of that writing, even though it might have been from the same era, but it was clear, okay, well, this is more like Francis Bacon. This is, so it had that understanding where it could actually get that subtle difference. So that's where model size really does play a role because there's only so much you can represent.
Thank you.
Absolutely. Other questions?
Do you know, Jesse, do you know, can you explain how, like you said, O3 uses a lot of tools.
Yeah.
How does it, how does it know? I've always wondered, how does a language model know which tool to use? Like, is each tool vectorized somehow? Like, or there's got to be some linkage where it says, okay, this is my prompt, this is what my next task is, and then somehow it's got to find a tool that's similar. And I'm just curious on how it does that.
We're going to be certainly getting more in depth on this next week, but it can be beautifully stupid. It can be beautifully stupid, which is I'm going to tell you about a tool. Whenever you're asked about mathy things, be sure to get the numbers out and put it into an equation and then call this tool, which I'm calling calculator. And here's how you call calculator. Here's what the API call actually ought to be formatted as. So I want numbers, operations, and then call calculator for any mathy things. Quite literally, you could use the description for a zero-shot training of when to call a calculator, right? Because it knows what mathy is. It knows what the numbers are. And because it knows all of that, art has that representation. So it can be very high-level representation. For other tools, and especially when you want to call tools appropriately when you're reasoning, then you might want to do reinforcement training of saying, hey, whenever you're asked about things and you're not doing so hot in answering, do a search. Like if you are coming up with stuff and you're being inconsistent in your answer, and I don't know if you've ever done this, I've done this with me, where I'm beginning to answer, I'm like, well, I'm not making sense to me. So let me stop here and say, I don't know, right? I certainly have done that before, right? Answering, I thought I was going to do well. It's like, you know what? Let me call an audible. I actually don't know. So let's go look this up. That requires more training for the model to recognize when it's in that state, when it's being inconsistent. That's where reinforcement learning comes in. But the more straightforward the tool use and the clearer it is when you're supposed to be using it, the more likely you're going to be able to just like say it. Like coding tools for it to write its own software to solve something might require some more training because, call this tool whenever you need to write a computer program to solve something. Maybe not. Sanjana.
I'm just curious, like, how do you compare the different models that are out there? Like, for example, if I want to take a task like fine-tuning an open source model, like what sort of metric would you use to pick like which model would be the best, especially if you're not looking for something that's specialized yet, but like I guess something other than I guess size and whether that would take less time to compute on your computer.
Those are all good things to keep track of and to think about because it doesn't matter if the model is great if you can't run it, right? So what's most important is that you come up with a metric that reflects the actual job to be done. So the closer this is to the actual job you're going to be undertaking, the better. So if this is business related, right? And you're trying to answer questions, right? Um, the metric may be, um, is that answer found somewhere in the manual, right? And does it match what was in the manual? Then you might have another one which scores how conversational was it. So you might actually have a the easiest way is if you're asking to solve math problems, like, well, you can solve that math problem using other software and tell whether it did it right or not. For other ones, it may be harder to measure. The funny thing is that one of the ways to measure this may be with an even bigger, better large language model. So certainly I've used reasoning models before to say, judge the output of this small language model on how well it answered the question, and then score it on a scale of 0 to 5 on how well it did, and give me the reason why. Now I have a way of measuring whether the additional training I've done in that model has made a difference, whether the prompting has made a difference, whether adding a tool has made a difference. You have to have some way of measuring fairly reliably and without a great deal of cost whether you're moving in the right direction. Um, so the metric really is up to you, and there are lots of different ways to operationalize it, but that's actually a really good question. You need a metric in some fashion that is as close as possible to the actual use of the solution that you can get. Other questions? And folks, I'm going to hand it off to Umang now because I'm going to have to hop onto the other meeting. But Umang, if you wouldn't mind taking the additional questions, thank you all very much for your questions and for your time. I'll see you all on Wednesday. And Umang, I'm going to turn this over to you. There you go. You are now going to be host.
Awesome. All right, other questions? Yeah, go for it, Daniel.
Yeah, sorry. Thank you so much. Like I said, I've got like 70 questions I want to follow up on, but I don't want to, just totally monopolize your time. Other people got important stuff too. But so I keep thinking about this issue of tone and what to the AI model is just tone, right? But if I say like answer this question and do it conversationally, what I want to know is at some level has the underlying probability flipped in some way, the probability of seeing a given token or in the output? Or is it the case that you've got sort of like a basic answer and it's going to do some sort of additive path? So for example, what I mean is like I ask it, I say, please explain the evolution of snake to me, but do it in a conversational tone, okay? Or make it as much like conversation as you can. What I notice as a linguist is it seems like it's got a basic outline for its answer, and then it has a certain set of what it considers to be conversational features, rightly or wrongly. And it just goes in and it peppers, wherever it can stick in a conversational feature, just sticks one in there, irrespective of, from a linguistic perspective, what that conversational feature is doing, functionally, how it's affecting the grammar of the sentence, how it's affecting the discourse as it unfolds. So you get things like discourse markers just used extremely inauthentically. And the AI has just shoved a bunch of discourse markers in there where they shouldn't be. And, probabilistically, they shouldn't be there, but they're there. And I'm just wondering, like, how did that happen? Again, is there something, is like a two-step process of first it composes an answer and then it does like a tone sweep? Jesse's answer would suggest that's not the case, but I don't see how you get the kind of output that it produces if there is some sort of fundamental resetting of probabilities when you ask it to do something conversationally based on the context that came before context.
Right. Yeah, it's definitely not a two-step process. I do believe that, just the activation of the features causes the end probabilities to just turn out differently, and that's what's leading to a different answer. It responding in a certain way that just seems linguistically improper could really just boil down to some of that last reinforcement learning with human feedback that it's gotten, and just a little bit of, so all of these models go through some bit of sort of training to teach them how to talk in certain ways. Um, like um, it's just some part of reinforcement learning where they basically teach the model that, when you're asked something, respond kindly, and these are examples of what kind responses are, and these are examples of what unkind responses are, and then the model is basically penalized or rewarded based on, whether it came up with a good response or a bad response. So a lot of that could really boil down to what that training set looked like. That happens a lot in, I know they sit there and curate these large data sets of what a good response should be. So it could really just boil down to that, okay, those responses just happen to be not quite right. Because I'm assuming, OpenAI isn't sitting there hiring linguists to ensure that it's absolutely correct, but they're more like, okay, does this sound right? They've sit there and curated this sort of essentially a data set.
Okay, but can I show you? Can I share my screen?
Sure.
Okay, 1 second here. So please forgive the XML, but this is a real conversation. So this is a transcript of a real conversation. And what you see when you look at it is it's really hard to understand what they're talking about because you don't have that context. You don't know what's in the physical environment. And there's tons of pronouns. There's lots of deictic pronouns referring to things in the environment. There's lots of names. The names are taken out here because it's all anonymized. But first and second person pronouns. There's lots of like hesitancies and false starts. So good. Let's see, where does this go? I'm just going to put these. Would you mind if I just do this really fast? So you have this clause that starts out with one grammatical structure and then goes to another one. So like all of those things should be learned, right? Like the way that you start with one grammatical structure, you move to another. The frequency of pronouns, relative frequency of pronouns, that's stuff that's recoverable, right, through just statistical processing. So then I asked ChatGPT to give me a conversation, and it doesn't look anything like that, right? So I don't think this is a reinforcement thing, right? There's some, okay, so what does ChatGPT produce? So it produces, little superfluous add-on comments. It says "mintive" is a conversational contraction. I disagree, right? You don't have that sort of density of pronouns. You don't have the deictic reference. You don't have most of what you get. But when I ask ChatGPT, like, what's conversational about this, it goes through and it tells me what it thinks is conversational, right? And so again, and there's like something in every line. Like, if you look at, there's like 2 or 3 things in every line. Okay, so why is it that we have 2 or 3 things in every line? It's always 2 or 3 things in every line. And again, it just seems like there must be some. Again, it just wouldn't work that way, right? You'd get a much more random distribution, 1 thing here, 10 things here, right? So does any of this, am I making any sense? Am I just like shouting at the wall?
No, it's interesting. Yeah, I understand what you're saying, and it's definitely not like what you showed right before this. I mean, from a purely technical standpoint, yeah, it's not a 2-step process, but this is very interesting that it is so almost systematic about making this conversational. Um, I
And then there's another part to it too, which is that so it seems very additive, right? So when I ask it to make something conversational, what it seems to do is kind of identify what it thinks is conversational, and then again just add conversational features to it. But actually, these conversational features come at the expense of written features, right? So if something is very written, very academic-y, very composed, you'll see different kinds of complexity. You'll see different kinds of grammatical structures. So the conversational structures that appear should come at the expense of those written structures, but they don't. So the things that should not appear here still appear here. Does that make sense?
Yeah.
And I don't see how that would be the case if it were purely just looking at statistical regularities, because those statistical regularities would be picked up on in the input. So again, the reason I'm harping on this is just because I'm trying to figure out why. Like from a linguistic standpoint, is there like an AI grammar? Is there like a grammar of ChatGPT that it somehow?
That definitely, I know for sure there is a grammar of ChatGPT. I've gotten like, just texts from other people and I can immediately identify when it is ChatGPT. It 100% has a style of talking, and I'm guessing it has evolved this style of conversational talking as well. I'd be curious to see, how much can you force it to become like a human conversational conversation with just prompts and examples. I'm
Yes.
sure at some point it's been maybe, guided to respond in certain ways. It goes through like very, very rigorous response training. And so maybe somewhere along the way, it's been really essentially told to speak in certain ways only, unless asked otherwise. And it just goes back to that same style over and over again. That's the only thing that comes to mind. Nothing like in the architecture of the model tells me that, it's going and like grabbing parts and only adding them in certain ways. I think that's more like this um, feature that's kind of evolved, and these things happen all the time in these models, just things that we didn't train into the model, but it's just kind of learned how to do or does things in a certain way that are somewhat unexplainable. That's kind of like the black box part of these models, is really figuring out why these random abilities of it just happen. I think Jesse will be able to answer a little bit better about this, but I do think it really comes down to it being like very rigorously trained into talking in a very specific way.
Mhm.
Um, but it is weird that it's even like it's being so systematic about it. It does. I agree with you. It sounds like it comes up with a response and then goes back and makes it conversational by adding things in and out. Like it does when I've used ChatGPT in its like conversation mode, it is a lot more human than when it
Mm.
is just in its text mode, which is also very creepy. So I would actually kind of play around with that voice mode and see how you feel about that with respect to how it comes up, and see how different it is, if it really is still, very systematic like this, or it's more random. Um,
So in that case, Umang, could it be what's happening is because the language that you produce is conversational, that's going into context, and then that context is pushing it more toward actual conversation output. Whereas here,
Mhm.
my input for it is written. So even though I'm asking it to be conversational, the output it's producing is actually quite written.
Definitely. So I do think you could force it to talk a lot like that document you just showed us. If you were to just give it a chunk of that document and say, I want you to talk like this
Mm.
from this point onwards, I think it would do a relatively good job of that. Like we've played around with the idea of having it sound like certain people, or having it write like certain people. For example, we had a French Revolution project where we wanted it to mimic the writing of George Washington writing to Lafayette. And it did that really, really well, because we gave it lots of examples of George Washington's writings and some examples of letters between George Washington and Lafayette. So it gets really good at mimicking things as well. So I do think maybe, it has a preference and its own dialect when left to its own devices, but when you force it to talk a certain way, it picks up on that very, very quickly. I'd kind of play around with that a little bit and see what you get from that.
Yeah, very good idea. Wow, thank you. Okay, I can take a lot more of your time, but I think I need to process and do some more thinking. I appreciate
Yes,
it.
I'm also going to think about this. Yeah. Other
Okay,
questions?
I'll see you Wednesday.
Awesome. See you Wednesday.
Yeah, Umang, I was thinking I'm trying to use this OpenAI agents SDK that came out recently, and it's extremely brittle. Like it's I don't know
Yeah.
if you have you used it at all?
I have not used it yet, but I'm not surprised that it's brittle. Agents are difficult to work with in the first place, but Shara is going to go over lots of agent stuff in the last week, and I'm very excited for that because I'm more on the RAG side of things. I spend my time building that kind of stuff, but Shara's worked a lot with agents, and so it's really, really exciting stuff from there. But yeah, if it's new, I'm not very surprised that it's brittle. Even now, even in just regular chat GPT, the behavior of how its agentic functions and just its ability to use tools is not the best in my opinion. As Jesse said, sometimes you will ask it the simplest question and it'll go and do a long Google search before responding. And it's yeah, it's definitely not a perfect system.
When you try to do it in ChatGPT, is that through like those personalized GPT things, or
Just like even just its like regular tool use, but yeah, in GPTs as well, getting it to actually do tool use through the configured GPTs can be a challenge sometimes. I've only done it
really?
once.
Okay.
I've only done it once and had it call an API, and even then, sometimes it would call an API, sometimes it wouldn't. To be fair, it was way back when, I mean, okay, maybe 8 months ago, which does feel like way back when with respect to these models. But yeah, it can be a challenge to get it to work, especially in the OpenAI environment. When you take things offline and you're just doing everything locally and it's all in nice Python code, it tends to be more reliable because you
Mm-hmm.
can really almost force it to every time call an agent if that is the kind of setup you need. But here, yeah, I definitely do see irregularities in the way these models use tools and how you can set them up to use tools in the GPTs.
It's interesting because I'm doing this right now, and I have two web search tools I'm playing around with, and then if I use one, it gets me. This probably isn't surprising, but if I use the ChatGPT built-in web tool or the OpenAI built-in web tool, it gives me links that are broken. It doesn't give me the JSON format I want. But if I use this other one that's called Link Up, that's, I guess, reputable as being one of the better web tools out there, web search tools. That's what I meant, web search tools. It works perfectly. It'll give me very good resources, recent resources, and it will give me the JSON output that I'm trying to force it to do.
That's good. I'm
Just
glad they've made that. But is that within like a custom GPT?
no, I'm doing this all in Google Colab right now.
Oh, okay, cool, cool, cool. Awesome.
I'm just using the OpenAI
Okay, you're just using
agents SDK. So like it's called OpenAI agents, I think. OpenAI dash agents is the library I installed.
cool. Yeah, I have not looked at that yet, but I think it because you're having it use this like other tool that so I mean ChatGPT has been kind of taught how to use its own built-in tool. It went through some amount of training so that it knows to use that tool. But when you're, I think, giving it access to another tool like this, you can it kind of forces the model to like follow that set of documentation really, really closely. Um, and I think that's kind of what you're seeing. Even like I've seen, if I ask ChatGPT to just respond in a certain format every single time, just verbally, it struggles to do that. But the second I throw in, okay, here's JSON formatting that you must respond in, it is always perfect. So I think giving it like, the structured, especially working with sort of structured data, especially JSON, really, really enforces it to kind of go in and fill in the blanks and then use that format tool. That's kind of what I've noticed. I, again, don't really understand because they don't really tell us how these tools were developed or trained on. But I think just, if you have a good, robust set of instructions and a good pathway for the model to follow using some sort of structured data, it tends to work better.
And then to that point, I've not been using Pedantic that much. Would you prefer Pydantic seems to be, is that an alternative to like JSON, but a much more reliable thing than JSON, or how should I be thinking?
I have again not used that much. I stick to JSON because that works well for me.
For RAG, it works really well. Sure.
Yeah, yeah, it does. So yeah, I've not used that, so I really can't talk to that.
And so since you're dealing a lot with RAG, what's been your recent, I mean, there's so many papers coming out on RAG and knowledge graph RAG or whatever. what has, and no, again, I'm sure one size doesn't fit all, but what's a couple papers that you could point to that we, to say, hey, this is recent stuff that possibly is improving, the RAG process.
I don't have papers, but I do have a GitHub repository that I've been kind of keeping up with, and they just do a really good job of
Okay.
keeping with all sorts of stuff. And we'll kind of go over some of this stuff as well in, I believe, next week. But this is a good repository that tends to keep up. And we'll go over a good chunk of these in the next week, actually. Um,
Okay.
but they have, lots of stuff about graph rag in here as well. Generally, that's kind of like the latest thing. Graph rag seems to work really, really well. And I do think so. I would say for, the tools that I've used, I haven't seen like the most noticeable difference. Because honestly, for RAG, the more I've worked with it, the more I kind of realize you just need a really, really good, robust set of instructions and prompting, and obviously good, like intelligent chunking of your data till your data is embedded correctly and well, and you're kind of telling the model exactly the information that it has access to. It does a really good job of kind of sticking to that, not hallucinating. Um, but I think prompt is everything in my experience.
Really? Okay, so I would have thought the second part you brought up, like how do you chunk this thing so that, because it just always bothered me that the basic ones would chunk just randomly,
Yeah, like
whatever,
1,000
a
characters or
thousand
what.
tokens or whatever. Yeah, 1,000 characters or whatever, and it just, and then there's some overlap or something like that. So like that just sort of, you're not getting any sort of meta data or anything
Yeah,
like, or
that,
it's
that starts falling apart the second you start working with structured data, like a CSV file. Now imagine, you take a CSV file, it's a text document, which the first line of the text document is the row headers, and the rest of it is all numbers separated by commas. Second, you break that up into chunks. The
yeah,
first,
that doesn't.
all the context, the rest of the chunks have just numbers, which basically mean nothing at that point. If it just grabbed a single chunk that wasn't properly broken up, it's going to struggle to really work. CSV files, it just falls apart. So there are now ways that you can deal with CSVs in a better way that breaks them up into a way that makes sense. Um, But, if you just have large documents, the chunking matters a little bit less. What I've kind of started playing around with is actually using different vector stores that contain different sort of levels of information. So, for example, for one of our projects, we have these, climate action plans that are hundreds of pages long. Even if I want, I could, have a large vector store and be able to retrieve a bunch of chunks and say, how do people deal with sea level rise? It just becomes so difficult to get a good response from it that is well sourced and documented and has the details that I need, that it started making more sense for us to first take these documents, process them, generate like these robust reports out of the documents themselves, and then create
Mhm.
a store that's just a collection of the reports that we generate.
Sorry, the last part, after you create a report on a document, you're saying like a
Yeah,
detail,
sure.
a nice
Right.
outline or whatever, then what
Exactly.
do you do?
So we just take that report itself and then generate a bunch of reports for all of the plans, and then just create a vector store that is that one collection of all the reports. Now it's able to basically, now we those reports are very, very detailed, but they're only like 3 or 4 pages long, and they have like all the relevant information from these 300-page documents that, otherwise have information that's not that's more fluff. You know, there's images and there's like other legal frameworks that the model already kind of knows about. Like it knows that this specific law in California means this thing, at least in our experience. So we just gave it access to these reports instead of these larger files, and its responses were just so much better because we were still getting detailed, rich information, just it was condensed and then given to the and then put into RAG. That just worked better. That's an approach that worked for us rather than having it, you know. The other alternative was have it do a retrieval one at a time for each singular climate action plan, and that just becomes computationally very expensive. It just takes time. It's not like computationally expensive, but it just takes time because it's doing so many retrievals. And so we just figured that, you know, generating these rich, pre-processing your data, generating these rich reports is a good way to kind of get around that issue.
So do you vectorize each of those reports into like several chunks? Or do you
Yeah,
just do
so
one vector for each report?
because they're like smaller reports, we just kind of broke them up into two chunks. So each
Okay.
report was two chunks, and that's all it needed.
And
So it was,
how many dimensions?
um,
Like how
so
long are the vectors roughly?
we just use like OpenAI embedding. So whatever those embedding
Okay.
matrix, like 700.
Hmm. And then you never really ever refer to the 300-page documents then?
So then our goal is, you know, we can get the tool to give us like this it's able to answer these higher level questions that span across multiple, you know, plans. We got it to respond well to that, but now imagine if we wanted to do a deep dive into that, we're basically adding agentic capabilities there so that now, you know, if you were to say, okay, following up, I'm very interested in the LA plan specifically. Now we're working on an agent that can go in and just specifically use the vector store that is defined for that singular plan. So then it'll do retrievals separately for that.
So are you storing the vector store for each of those 300-page documents already, or are you asking it to create the vector store on the fly?
It's already pre-processed. So like I have this large folder on my computer that's just like multiple like vector stores. One's like one vector store for each plan. One's this like larger vector store that has just the reports. One is, you know, another different type of vector store that is all the plans in California because, you know, where we want to ask questions specific to that, but we want more detailed. So we just created a smaller vector store for it to search across with better chunking. So we kind of played around with, you know, what each vector store contains and then query them intelligently.
So is the secret sauce to creating those reports, those 3 to 4 page reports, is that I mean you have to design yeah, I mean
You
it's not
kind of
just
need to know
the
what,
prompt. You have you each of them you just have to design a template of
right,
some sorts.
exactly.
But
So, you know, we had a couple of domain experts who've read hundreds of these climate action plans over the years. They know what these contain, and they kind of understand that there's, you know, all of them have certain sets of information, and these are the sets of information that would be most important to say somebody who's working on a new plan. So we came up with a template. We developed a prompt that kind of told, okay, now you want to generate a report for this specific document in this template. It grabs all the information. Then we have a nice report. But you got to know what those documents contain. You need to know what you're looking for. You can't just say generate a report and expect it to be the rich detail that you're looking for. You kind of need to know what is the rich detail you're looking for. Yeah.
Okay, cool. Thanks a lot, Aman. Oh, see you hopefully Wednesday.
Yep. See you Wednesday.
Okay, bye.
All right. We have a couple more minutes. Any other questions?
Yeah, show us your shirt. What's it say? I can't read it all.
It says first they steal your heart, then they steal your bed, and so it's just a bulldog on there. And then this is my bulldog sleeping right there.
Nice. Dogs are great.
Oh yeah, love them.
Umang, thanks so much.
Of course. We'll see you Wednesday. All right, Victor, Samir, any last questions before we close out? All right, if there's nothing else, we'll see you Wednesday.